Good morning, everyone. In the previous class, we started our analysis for the different timing matrices for the sequential logic circuits. Okay. Let us start again and try to understand the different concepts and different parameters which are associated with the sequential circuit timings. Okay. So, suppose basically we know that the sequential logic circuits are nothing but if we somehow connect the output with the input, then in that case we can make it the sequential. Like if the input depends on the present as well as the past value, then we can call it the sequential circuit. Okay. So the simplest example of the sequential circuit is like if we have, suppose we have a combinational circuit like this, having some inputs, some outputs. So what we can do, suppose, so I have some feedback path. This feedback path can be memory or memoryless. It can be anything. Like, so I'm considering here the feedback path is memory register, which can store the present output of this combinational logic circuit, and that can be utilized to when we are operating the signals, like input signal in the next state. Okay, so these are the registers which can hold the present output values. Okay, so if we have a feedback something like that, we can call them the sequential circuit, or basically this is nothing but this is the finite state machine. Okay, so this is the general diagram of the finite state machine, where the finite state machine is nothing but this is the part of the sequential circuit, right? So we have already studied these things. Now, to understand the working of the finite state machine or the sequential logic circuits, we need to come up with something which is really very important, right? So here, if you see, this particular finite state machine is the synchronous one. How we are deciding this is the synchronous one? Because we have a clock signal and all the registers are controlled by this clock. So we can call it like this is the synchronous one. Okay, if there is no clock on the register, then we can call them the asynchronous kind of sequential circuit. Okay, now let us try to understand a few things which are really important. Suppose because this particular finite state machine is clock dependent, so let us first draw the clock. So suppose I have a clock which is varying from high to low in between this one. Okay, so to understand the working of the register, whatever here we have a register over here, and to understand the working of this register, basically three important timing parameters are really very important. Okay, let me repeat it again. If I have to understand the working of this register, how this is storing the data, how it is transmitting to the, for the, how it can be utilized for the next stage. So to understand all those things, we have to understand few timing parameters that is associated with this register. Okay, so let us discuss one by one all those parameters. Okay, so suppose I have an input of this register which is changing something like this. Okay, if you see clearly, here we have an input initially which was high. Okay, but it changes its state from high to low. Okay, there was some change in the state which is from high to low, but during the clock it was at logic low, because this register is the age triggered. If you see here, because triangle is given over here, so this register is nothing but this is the age trigger. So this will work either on the rising pulse or on the falling pulse, because this is a positive age trigger. So it will always work when there is some transition from low to high in the clock one. So even though input has been changed, they will wait up to this time when there is some transition in the clock from low to high. Okay, so this is one of the things. The second thing is that, yeah, this is nothing but this indicates if there is n number of bits, then this indicates the transition. Here here we have the stability, and whatever the input that will be transferred, and it will not be reflected like this particular state is nothing but this is the stable state when we will get the output one. Okay, and this particular transition in the D indicates like transition state in the input signal. Okay, now few things that we need to understand from here. Okay, yeah, one more thing, like because we have a register, we have a clock pulse. So in the register, we have a input D, we have a output Q, and we have a clock. So we already understand what is the clock, what is the D. And now let us try to see what is this Q. Okay, so this output Q is the function of this input as well as clock, and it also depends on what is the delay of this combinational logic, right? Because this combinational logic delay can provide the input, and if there is more delay, then the input at D, it will take more time and the output will be reflected after a certain time period, right? So this outputs and other thing, all this depends on the this combinational logic circuit as well. Like see, the output, delay, and every parameter of this finite state machine depends on this register parameter, timing parameters, as well as the timing parameter of this combinational logic circuit. Because if the combinational logic circuit is very slow, which is not able to provide the output on time, so the register, even though register is activated, like the it need to wait for some period of time to change it into the output form, right? So it can, so this is the important thing which we should know. Okay, so by keeping all these things in our mind, let us try to define few things. Yeah, I just told you here, it indicates the data stability. If there is some, yeah, these all are the states where the data will be stable. Like this is the region where the data will be stable. This is the region where data will be stable. This is the region where data is stable. But here, during transition, the stability is not there, right? So this is in a transition mode, not in the stable mode. So the data stability is possible if the logic is fixed, if there is no transition. Okay, so that is why we are calling it the data stability. Now let us talk one by one. So I just told you, because this register is nothing but this is the positive edge trigger. So we need to consider the reference where the clock is changing from low to high. So here we will consider the reference, because yeah, because this is the positive edge trigger. So this is the time when clock is changing its state from low to high. Okay, and this is the positive edge. Okay, so if this is the positive edge, so here we will consider it as a reference. Now, because the data was activated well before this rising pulse, so we need to consider some time, like what was the time at which the data was changed, and it comes under the stable state, and it was waiting to convert or to have a clock with the positive edge. Okay, so that time we need to calculate, and we call this time as a setup time, which is a TSU here. Okay, so this is nothing but this is the setup time. That means, what it means, simply the like the setup time is a time that the data input must be valid before the clock transition. Okay, in this case the clock is like positive edge trigger, so there is some transition, there is some data, so data is valid after this value of after this one, and then it is waiting for the clock. So this total time period, we call it the setup time. Similarly, for example, if the data is changing, like suppose let me consider a few things. Let us assume I'm assuming like data was something like this. Okay, but once the data is like this, and again there is some transition, something like this. Okay, and it is changing something like this. So I need to consider at which the data is fixed, it is stable before this rising pulse. So I need to calculate with respect to this time, not this time. So the last transition means simply I have to calculate the setup time. I have to consider what was the last transition in the data input and the rising pulse of the clock. So that time decides the setup time. Okay. So basically setup time that should be as small as possible. It's not like that the data is in the register well before, and it is waiting to activate the register. So this is not recommended. The setup time should be as small as possible, so that once the data is converted, immediately it will do some action based on the circuitry. Okay, so this is important thing. Now the second parameter is, because here we have a clock which is active, which is changing, like positive ways. Okay, and because we are saying this is a state when the data is stable, but might be once this is activated, the data may change again its state. Okay, so data is changing its state again. So there is one more time at which the data is changing its state from the stable one. So from stable to transition, there is possibility like the data input can have a transition state. Okay, after this rising pulse. Okay, so we need to define this timing as well, up to what time this is holding the data. Okay, so this is really very important. Okay, so this is time, we call it the hold time, th. Th is nothing but this is the hold time. So this is the time up to which, like, the means the whole time is the time that data input must remain valid after the clock age. Okay, so this we call the hold time. Okay, suppose very important thing, like if I want to utilize this circuitry for a particular application, and if hold time is very small, okay, if hold time is very, very small, and might be the execution time of the circuit on which we are using this data is very high, means it is taking too much time to execute this one. So if it is less than th, then it is perfectly fine. They will get it as a valid state. But if the execution time is more than this whole state, so what will happen? It will get this data input, like the secondary circuit will get the data input, and before execution, before operation, might be the data will change, and that may lead in the failure or malfunctioning. Okay, so this is really important, like what kind of circuit we have connected here, and what is the response of this circuit, and what is the hold time. So the hold time should be the sufficient enough so that it is able, or the circuit on which we are providing the input is able to perform the operation. Okay, so this is important parameter that we should consider.
Hello, sir.
Yes.
Sir, that point, can you repeat again, that if the th is that th should be large, otherwise then the
Okay, fine. So let me repeat it again. Suppose I have a circuit, like let us assume this is the resistor. Okay, this is the resistor. Let us assume the internal delay or the operation time of this resistor is, let us assume 3 nanosecond. Okay, for example, the operation time of this resistor is 3 nanosecond, and let us assume the whole time is only 1 nanosecond. Okay, what it means, it can hold the data for 1 nanosecond, and we know that the operation time of this delay, like it will take this much of time to operate on this input, and that will take 3 nanosecond. So even like, because it is taking 3 nanosecond and the data is on this state for only 1 nanosecond, might be there will be some change during the execution by this register only. Might be this will not be able to operate properly. Okay, so this is the problem. Okay, so like this time, like operation time of the circuit on which we are applying, that must be at least less than the whole time, so that we can transfer the valid states. Okay, you got the answer?
yes, I mean D2Q, for that to happen, the D should be valid at least for 3 nanoseconds.
Yeah, at least for the time period on which we are providing this input, right? So this is important. Okay, so this time we call it the hold time. Now another time which we can define from this timing diagram is the a third one. Like, see here, let us assume initially the out, like, yes, this is a register and it will operate based on the data input whatever we have provided. Okay, Now what it will do, there is something like because we have provided there may be some propagation delay of this logic or this register. Okay, whatever the register we have, there could be some propagation delay, which I was just saying, like it will take some time to execute this one. So what will happen if the propagation delay is uh, uh, and that is defined with this one, like the transition time and the on which the data is on the stable state. Okay, so this is the time which we call the TCQ. Okay, TCQ means the this is the worst case delay. Like assume that the setup and hold times are met and the data at the D input is copied to the Q output after a worst case delay. Okay, so this is the time at which the data is output to the Q, and that we define as a propagation delay, and that is denoted by the TCQ of this register. Okay, so this is important. So this is the propagation delay of the register with reference to the clock. Okay, so this is the third parameter. Now, other than these things, we also need to consider few parameters which are really very important based on this logic, because I just told you the complete function of this finite state machine depends on the register operation as well as the combinational logic circuit. Okay, so what are those parameters? That parameter is the one parameter which is this one, TP logic. TP logic is nothing but this is the propagation delay of the logic which we have connected over here. So TP logic is nothing but the this is the propagation delay of the combinational logic whatever we have. So this is the TP logic, and this is also equally important, especially while defining the delay of this finite state machine. I just told you. Okay, so this TP logic is nothing but this is the propagation delay of this logic whatever we have used. Okay, so if the propagation delay, like there is one more parameter which is really very important that we should consider, like the minimum TP logic, like the minimum propagation delay of this combinational logic can also be defined as a TCD. Okay, TCD is where the TCD is the clock to input, like because see, we have provided the clock and then combinational logic circuit will start working and that will provide some input to this D, right? Because this combinational logic circuit will operate. So that minimum minimum TP logic, we call it the TCD, which is clock to D delay. Okay, so the delay between clock and D, and we call it contamination delay. Okay, this is really very important. Like see, TP logic could be anything that depends on the logic, the delay of this combinational logic circuit. Okay, but if I want to use this output as an input for this register, in that case, I need to fix a minimum number of delay, minimum certain delay that is sufficient to execute the input or the output. Okay, in that case, we have to come up with the minimum delay, which is the TCD, means the clock. I have provided the clock and I'm getting the input D to this register after the execution of this combinational one. Okay, so that minimum delay is TCD, and we can call it the contamination delay. So this is also one of the important parameters. So these all are the 5 different components of timings for the finite state machine. First 3 timings are related with this register, and next 2 logics are related with the combinational logic circuits. And if we combine all these things, all 5 these delays, all these 5 timings, then this becomes the timing parameters for this whole finite state machine.
Sir,
Okay, yes.
sir, I didn't understand this TCD.
Okay. Okay, TCD. TCD is the okay, let me highlighted. Let me explain what TP logic is. TP logic is simply like whatever the input I will provide here, this combinational logic circuit will take some time to give some output. Okay, and that we are calling it TP logic. Okay, now what happens if this register will be executed? Yeah, this register will take this as a input D of this combination logic circuit, because this combination logic is not clock dependent, right? Okay, so even though this combination logic circuit has given the output, this will not take as an input once this clock is activated, right? So once the clock is activated, and now this will start taking the output from this combination logic, and that will be treated as an input. So the time delay between this clock and the input D is called contamination delay. So this is the minimum time required for this one, like so. This is the minimum time at which this register can operate. Okay, so this could be even more than that one, but that way we cannot call it the TCD. But once the clock is activated, then we can it might be the even though clock is activated, the combination logic circuit is still in process, and that will give some output certain period of time. So the time difference between the clock activation and the output time at which we are getting the output of this combination logic circuit, we call it the contamination delay. Okay, there is a slight difference between these two things. This TCD depends on the clock activation and the time at which we are getting the output from this combination logic circuit. But this TP logic is nothing but this is like whatever the input I have given, and I am getting the output. Okay, so it does not depend on the clock. It simply depends on the input and the output. Okay, so this is slight difference between TP logic and TCD. You got the answer?
Yes, sir. I understand.
Okay, perfect.
Hello,
So,
sir.
yeah, any other questions?
Sir, in this graph that you have drawn, the D that is the input that the D the data stable, उसका output जो आपने red में data stable दिखा है उतना time के बाद आ रहा है, यही that is right?
Yes, yeah. So this is what we are getting the output after, because this is the we have provided some clock and we are getting, so this is nothing but this is the delay of this register. Okay, so this propagation delay of this register, this indicate the propagation delay of the register.
Sir, means the green data stable, uska output is the red data stable, right?
Yes. This one is reflected here.
Okay, sir, and TP logic means, sir, the combinational logic जो भी AND gate, NOR gate हमने जो लगाया, all that उसका सबका delay जो sum है, that is TP logic, right?
Yes. So whatever the structure is inside this combination logic circuit, the delay between this input and the output is the TP logic. Okay, without considering the clock of this register. Okay, and TCD is when we are considering the clock, then it becomes a TCD. So this is the slight difference.
So considering clock means once the output has come, but the clock pulse has not risen, so that much.
Yes. So even no. See, suppose what happens? Let us assume I have activated the clock. Okay, and I have changed the input. Okay, so clock is activated, and the input we have provided, and now this combination logic circuit will take some time to execute and to give the output. Okay, so the clock is activated and it is waiting for the input, but the combination logic circuit is not able to provide the logic because it will take some time based on the input. So the time period between the clock activation and at which we are getting the stable output here, that time is the TCD.
No, sir, could you repeat, like the clock was active, then that was fed into the combinational?
Yeah, so yes, so yeah, please ask the question and I will answer that.
No, sir, the explanation that you were repeating for TCD again, can you explain?
Okay, so let me explain it again. Suppose here we have a clock, okay, and here we have an input. So if we see the TP logic is simply the delay of this combinational logic circuit. So once we have provided the input, okay, it will start operating based on the input combination and the internal circuitry, and it will give the output, let us assume after time t. Okay, after a certain period of time. So that delay, we are calling it TP logic. Now, suppose, and here in this case, we are not considering the clock. Okay, now let us assume I have provided the input, I have changed the input, and even also I have activated the clock. Okay, so because I have activated the clock, this register is waiting for the next stage input. Okay, this is waiting for the input, but this combination circuit, because I have provided the input, it will take some time to give output, like time t. Okay, so this I think this register need to wait for the time period up until this combination logic circuit will not give you the output. This clock is activated, this register is waiting for the output, like waiting for the input, but this combinational logic circuit is not ready to give the output because of this internal propagation delay. Okay, so that we are considering like the TCD.
Yes, sir. So the inputs we gave, but after TP logic, only the input will be available, right? So TCD and TP.
Yes.
Logic.
So suppose let us assume. Okay, let me write few mathematical values so that we'll be able. Let us assume I have provided input at t is equal to 0. Okay, and I am assuming that this combinational logic circuit having delay of 4 nanosecond. So at t is equal to 4 nanosecond, I will get the output from this combinational logic circuit. But I have changed the input at t is equal to 0, and I want to get the output. Let's assume at t is equal to 1 nanosecond. I want to get the I want to utilize this register. I have activated this register, but because at t is equal to 1 nanosecond, we have activated this clock, and I'm expecting that this combination logic circuit will give some output so that I can use it for the register. But because it will take 4 nanosecond to execute it, and we are activating this clock at 1 nanosecond. So the 4 minus 3, that will be 4 minus 1, that will be 3 nanosecond, and that is the minimum time that I need to wait so that I can get the exact output of this combination logic circuit, which can be treated as an input for this register. So this 3 nanosecond is nothing but this is a TCD, which we are calling it the contamination delay.
Yes, sir. Yes, sir. Got it, sir. Now I got 3 nanosecond is TCD and 4 nanosecond is TP logic.
Yes.
Yes, sir. Thank you.
Okay. So okay, so this is all about the contamination delay and the different timing components of this sequential logic circuit. Okay. Now, if I want, suppose I have a finite state machine or the sequential logic circuit, and I want to calculate the delay of this finite state machine. So the minimum clock period that required for the proper operation of this sequential logic circuit, that must be is equal to or greater than TCQ plus T setup time plus TP logic. So this is really very important to consider the time clock period of this sequential logic circuit, and this is really very important question if we are considering the sequential logic circuit. Okay, so that depends on the setup time, that depends on the TCQ, which is the propagation delay of this register, and the propagation delay of logic as well, right? So these are some of the parameters which decides the minimum clock period for this sequential logic circuit. So this slide is really very important, and you should understand how the sequential logic circuit works, what are the different timing components, and how we can define different timing and the delay components. Okay, if there is no doubt, I can move ahead with the next thing. Okay, now let us try to design, like initially we designed like SR latches and other things based on the normal like we have a NOR based structure, and then we have feedback one of the output to the second input and the vice versa, and we try to replicate it in terms of the CMOS logic circuit, and we got some circuitry. We did it for the SR logic. Okay, and we know that for the D, if I want to make the D latch, in that case S and R must be complementary in nature. This is the simple structure, like we know that how to make the D latch from the SR latch. Simply connect an inverter in between set and reset input, and that will be nothing but this will be the D latch. Okay, but suppose I want to make a D latch somewhat more simpler than the what exactly here we have defined. Like see here, so here we have defined like this is nothing but this is the D latch, but the number of transistors and other things like this is the conventional way how we can design the SR latch. Okay, but if I want to make the D latch in other ways, so how it can be done? So let us try to understand those things. Okay. Yeah, this is the simple structure of the transmission gate based D latch. Yeah, these are the transmission gate. Yeah, we know that this is the transmission gate, and how it will work. Let us try to understand the things. Okay, so if you clearly see, like, yeah, let me go back to the previous one. Like if I have a clocked based, yeah, here. If I consider a clocked SR latch, in that case, the total number of transistors are here 12 transistors. This is not 11, this is 12. Okay, I made a mistake here. Okay, so here I have a 12 number of transistors. Okay, 12 transistors are here, and also like we need total number of transistors 12 here. But if I want to make this SR latch and I want to convert it into the D latch, so I need one more inverter. Okay, so that I can connect S and R with the complementary in nature. Okay, so the total number of transistors will be 14. Okay, so if I want to make a clocked D latch based on this conventional method, then I may need 14 number of transistors. Okay, but if because the transmission gate and other kind of logics are basically utilized when we want to reduce the area, we want to reduce the number of transistors. Okay, so in that case, how it can be done? If you see here, how many transistors we need? We need a total number of 1, 2, 3, 4, 5, 6, 7, 8, and 2 transistors for this clock complement. So total 10 transistors required for the D latch implementation if I am considering the transmission gate based latch. Okay, so this is really very important to consider. Okay, so the total transistor is equal to 10. Okay, so the total number of transistors will be 10. Now let us try to consider the function of this logic. Okay, so let us assume yeah, so this particular block is nothing but this is the transmission gate 1 and this is the transmission gate 2. Okay, so let us try to understand how this circuit works. Okay, so the case 1, okay, so the first case is if clock is equal to 0. Okay, if clock is equal to 0, then what will happen? Let us assume if clock is equal to 0, then this transistor will not be in on state. Okay, and clock bar that will give 1, so this will also be not in the on state. Clock is equal to 0 means this will be in on state, this will be in the on state. Okay, and how this circuit will work? So if you see the equivalent circuit of this one, so here I have an inverter, so I have one inverter, I have another inverter, I have taken some output Q from here, Q bar is here, and because this transmission gate logic will directly pass the logic, whatever here we have, and that will be connected to this one. So what I have done, I have connected something like this. So if you clearly see this particular circuit, this is nothing, this becomes the latch. This looks like a latch, because what we have done, we have connected two inverter in the feedback path mechanisms, and we are getting two outputs, Q and Q bar. And what it means, this circuit or this logic will be in the latch mode. So whatever the previous state was, either Q was 0 or Q was 1, that will be maintained. Okay, so if clock is equal to 0, in that case Qn plus 1 is nothing but this is same as Qn. Okay, and we call it the latch mode. Okay, so this is the first case. Now let us talk about the case 2. Okay, if the clock is equal to 1. Okay, let us consider the second case. If clock is equal to 1, what happens? Let us see. If clock is equal to 1, in that case, this will become 1, this will become 0. So this NMOS transistor, PMOS transistor and NMOS transistor is in the on state. Similarly, if you see here, because the clock is equal to 1, so this will be in the off state, this will be in the off state. So there is no feedback path. Okay, there is no feedback path which will exist, like TG2 will be in the off state. Okay, and TG1 is in the on state. And whatever the D input I have given over here, that will come to this point. Okay, that will be converted, means like Q bar will be the D bar, and again it will be inverted, and then at the output I will get the same. So whatever the input I have provided here, that will be reflected at the output Q with certain delay of these inverters in the transmission gate. Okay, so what we will see, like the Q n plus 1 is nothing but this is the function of D. Okay, so because it is not holding the data, and this is simply transferring the input whatever we have provided, so we call it transparent mode. Okay, so this mode of operation is the transparent mode. So these are the two logic states, or the two cases which we should consider for the transmission gate based latch. Okay, any doubt? Anyone? Okay, so if there is no doubt, then I can move ahead with the other kind of circuitry. Okay, so yeah, this circuit is really very simple. Like yes, so if someone want to do some research on the latch designing side, so what people used to do, people used to design some novel structure. They can replace this inverter with some novel inverter circuitry, and also this inverter circuit, so that they can reduce the hold time, setup time, and other things, so that the effective delay will be reduced. Okay, so these are some of the parameters which can be considered while designing the latches. So this is one of the scope where the people can do some research. Okay, so this is one of the variant of the D latch. Okay, now let us consider the second one. Okay, second kind of the D latch is the buffer D latch with the feedback inverter. Okay, how it works, let us try to see it. Okay, suppose, yeah, so this is the structure. Suppose I have provided the clock input to this one. Yeah, these two are the nothing but these are the transmission gate. Okay, so I have provided the clock here and the clock bar here. Remember, the clock and the clock bar in the first transmission gate is opposite to the second transmission gate. Here, if you see on PMOS side, I have provided the clock, and here on the NMOS side, the clock has been provided, and the vice versa. The clock complement is on the NMOS side, where the clock complement is in the PMOS side. Okay, so that this is really very important to understand the difference between these two things. Okay, now this is simply what we have done. We have taken the output from here and we have placed one inverter which is in the feedback over here. Okay, so let us see how it will, why we have provided the feedback, to match the forward and the feedback path delay. If you see the previous state, in the previous figure, what we see, the forward path delay is decided by these two inverters, okay, and one transmission gate, and the feedback path delay was decided by this transmission gate only. What it means, the forward path delay and the feedback path delay was not matched, they were not equal. Okay, so we need to adjust the sizing of these each circuits in a such a way that we can have a equal forward and the feedback path delay, and that will unnecessarily increase the delay of increase the size of some of the transistors. Okay, so to overcome that, we can consider the second variant which I was about to discuss here. So instead we can, because we know that the delay of the transmission gate is very small. Okay, so the transmission gate logic is very small, so one inverter is in the feedback forward path and one inverter is in the feedback path. Okay, so somehow we can match the delay between the forward path and the feedback path. Okay, yeah, a little bit area change is needed so that we can match this forward path just with this one. Yes,
Sir, can you go back a slide?
previous slide, right?
Yes.
Yeah, here.
Yes, sir. Why is that a problem that forward path and feedback path?
Forward path and feedback path. Okay, so let me assume, suppose I want to latch the data, hold the data, right? See here. So suppose I have provided some input. Okay, I have provided some clock here. So if the clock is equal to 0, in that case, that data will be on hold, right? See here. Here we have a D. Here we have a, let us assume whatever the let us assume it is Qn, and a Qn data whatever we have, and this is the Qn plus 1 complement. And so the important thing is, like, if it is in the transparent mode, so this one will be involved, this one will be involved, and this one will be involved. Okay, so it will take like delay of these three components. Okay, and if I am considering the latch mode, in that case the delay of this one and this one is involved in the forward path, and the delay of this transmission gate will be involved in the feedback path. Okay, so because the forward path gain and the feedback path gain could be different, and if they are different, might be the butterfly curve which we have drawn, that may be different because of the mismatch in the delay. So this is like that will be discussed when I will talk about the memory. So I think you need to hold for some time, some period of time. When I will discuss about the SRAM, then I will talk about some delays, some access time, write delay, read delay, so that you will be able to understand the importance of those things. But yes, for now, just consider like the feedback paths are different and the forward path are different, then that will give you some different kind of delay elements or the delay values.
Sir, in buffered delatch with feedback inverter,
yes,
sir, we added the NOT gate in feedback to match delay, but the transmission gate delay, that was
yes. So yeah, I just said I think these things. Okay, so let me go back to that slide. Okay, so here if you see, because I just told you the delay of the transmission gate is very minimal as compared to the normal circuitry. Okay, so what I have to do, I have to match the transistor sizing of this one in a such a way that let us assume the delay of this inverter is, let us assume T1. Okay, and the delay of this inverter is T2, and let us assume the delay of this inverter, this transmission gate is T3. So I need to match the sizing in a such a way that T1 must be is equal to T2 plus T3. Okay, because the T3 is the minimum. So I need to adjust somehow the inverter 1 and inverter 2, because the transmission gate are always made with the minimum size transistor. So we cannot match these things. Okay, so in that case, I have to manage the sizing of this inverter 1 and inverter 2 to make them equal.
Yes, I got it.
Okay, so yeah, so this is the thing which that can solve the purpose of delay. So here we have a clock, here we have a clock complement, and let us assume we have a 3 inverters. So let us try to understand the different cases. So suppose case 1. Okay, if I see the case 1, if clock is equal to 0. Okay, if clock is equal to 0, what it means, we are providing this NMOS transistor to clock 0, so this first transmission gate will not work. Okay, and if you see here, because these are complementary in nature, so this transmission gate will work. So what it means, this will act as a short circuit. Okay, so because this will start passing the logic. Okay, now we have so if clock is equal to 0, this is not going to pass. So whatever the state was there in the previous state, okay, so that will be QN complement will be there. Okay, and that will try to match again, it will create the latch and that will give the output. And here another inverter can be utilized to get the output. Yeah, even this is not mandatory, but you can use it to make more robust. Okay, so robustness can be improved, like the noise margin degradation, that can be improved. So this inverter can be added. Okay, so that you can get the exact output, not the complementary one. So this inverter is needed to get whatever the input we have provided, that I am getting the exactly same output, not the complementary one. So that I2 is needed here. I1 is nothing but to make the latch, and I3. So I1 and I3 are making latches, or the forward feedback mechanisms to hold the data, and I2 is utilized to give the exactly same logic whatever we have at QN, like not the complementary one. Okay, so for that purpose, this inverter 2 is utilized. Okay, so yeah, so this is the first case. So in that case, the QN plus 1 will be nothing. It is the QN, means the hold mode or latch mode. Okay, and the second case, like you can understand easily. So case 2, if clock is equal to 1, then this transmission gate will be activated. So here I will get input D, and that D will be decomplemented here and D here. So that will be transferred, because this is not activated. So this feedback path will be will not be activated. So whatever the input we have provided, so not complement, whatever the input I have provided, that will be reflected at the output one. Okay, so the QN plus 1 is nothing but this is the D. So this is what we call the transparent mode. Okay, so these are few things that we should consider. Now let us consider one more circuit. I will take 2 more minutes and I will finish it. I will finish this latch. Okay, so the third kind of variant is the the number of transistors. You can calculate how many transistors you need, like 2 10 2 and 2 10 plus 2 for clock inversion as well. So 12 transistors needed. Right. So for clock complement, you also need 2 transistors, right? So the total number of transistors will be 12. Okay. So yeah, so the next circuitry is the tri-state inverter based D-latch. Okay, so what is this tri-state inverter based D-latch? If you see here, these are the two circuitry which we call them the tri-state inverter. They are not the simple inverter, they are the clock dependent inverter, just like the dynamic logic circuits. Okay, so let us see how they are working. So here we have a clock and clock complement, and in the reverse kind of the clocks are given to the second transmission, the second tri-state inverter. Okay, so here I have a D. Here, whatever the D I will give, that depends whether the clock is activated or not. And accordingly, it will give the Q output. If clock is activated, in that case, I will get the Q complement at the output side. And that has been fed back to this one. Okay. How this will work? So here I have the first tri-state inverter and I have the second tri-state inverter. What happens, how this works, how this inverter works? Let us consider the tri-state inverter. For tri-state inverter, if clock is equal to 0, okay, TS1, I'm talking about a TS1 only, because the TS1 and TS2 are both are different one. So if clock is equal to 0, in that case, the clock bar will become 1, this will become 0. So this tri-state inverter 1 will not work. Okay. And if you talk about the TS2, because clock is equal to 0, so this will be 0. So this transistor is on, and this becomes a complementary. So this transistor is also on. So this will act as a normal inverter circuitry. Okay. So this will act as an inverter circuitry. So whatever the here we have like QN bar, here we have Q and here QN bar, and that is feedback. So that will act as a latch. So transmission gate, tri-state inverter 2 and this inverter will form a latch.
Sir,
yes.
So that depends on the whether what is the value of Q. उस पे depend करेगा ना?
Sorry, which one?
Sir, whether that TS2 will be on or not, that depends on Q. Is it?
No, this depends on the, this will be on. See here, let us assume the clock is equal to 0. Okay, so clock is equal to 0 means this transistor is on. So clock bar is 1, so this transistor is also on. Now if Q is equal to 0, in that case this will be activated. Okay, and if Q is equal to 1, then this will be activated. So either
Yes,
pull up or pull down, one will be always activated, right? So either it can, so it will, whatever the input I will provide, that will be complemented because it will act as an inverter. Okay, because both the transistors are like this, clock 0 and clock complement are 1. So now this depends on the activation of this transistor and this transistor, and which of the transistor will be activated, that depends on the what is the value of Q. Okay, so if Q is equal to 0, then the pull up will be activated, and if Q is equal to 1, then the pull down will be activated, and accordingly they will give the output Q bar. Okay, so this is how it works on the latch mode. Okay, now let us talk about the if clock is equal to 1. If clock is equal to 1, in that case, what will happen? This transistor will be in the on state, this will be in the on state, then whatever the input we have, it will complement the output here. Like if, because now this TS1 will work, so whatever the input I have, that will give the complementary to this one, and at this point I will get the exact input D, and because this is not activating, so at output Q I will get the output, and which is the same like the input, and we call it the transparent mode. So this is the simple working, like you can do some on and off kind of mechanisms, and you will be able to understand how they are working. Okay, so this is all about the tri-state based D latches.